Well, thank you. Thank you for the invitation. So I was told that we're being here for 20 hours. It's just as scary for me as it is for you. So I talk about enumeration of maps, and I talk on the blackboard. So there will be two main big parts in this series of lectures. In the first part, I talk about maps without an additional structure. And you can probably guess that the second part will be maps carrying some additional structure on them. So in this first part, it will mostly be old stuff, essentially what Stott was doing decades ago about this recursive method. And there will be a few more modern ingredients, especially dealing with the solution of the kind of functional equations he used to obtain, and also the use of Maple to play with all these things. And in the second part, there will be more recent things. Okay, so there are many or several methods to address the enumeration of maps. And I will list four of them, probably the main four. So first, there are the recursive approaches that use generating functions and equations on those generating functions. Then you've probably heard about the very successful story of bijective approaches. I can't spell. Then what? Another very successful approach and very powerful has been that of matrix integrals. And then there's also one fourth type of approach, which is based on algebraic combinatorics and especially the characters of the symmetric groups, which I denote by SN. So I will not take any risk in this series of lectures, and I will talk about what I know the best. So there will be a lot of this. There will be a little of that. And you won't hear in my talk about the last two methods for the shameful reason that I'm not familiar with them, which is, I admit, a bit embarrassing. So what should I say then? So I don't want to compare the charms and the powers of all these approaches, but if I had to give one reason why I will stick, or mostly stick to this one, in addition to the fact that's the one I know, let's say that at the moment, it is the only one, as far as I know, that can prove the following result. Which is a theorem due to Stott himself a long time ago. So at the moment, it's very likely that you won't understand what the objects I'm talking about are, but it will become clear that's just an advertisement for this recursive method. So this result says that the number say Cn of properly Q-colored rooted triangulations with n plus 2 vertices satisfies a certain recurrence relation, which I'm going to copy. So Q n plus 1, n plus 2, Cn is Q times Q minus 4 times 3n minus 1 times 3n minus 2, Cn minus 1, plus a convolution I plus 1, 3n minus 3i plus 1, Ci minus 1, Cn minus I, with some initial condition, which is that C naught is Q minus 1. So what does it mean? So we'll see just in a few minutes what a rooted triangulation looks like, essentially something like that. So in this theorem, you have a parameter Q, which is some positive integer, and it's the number of colors you are allowed to use to color the vertices of your triangulations in a proper way, which means that if you have two adjacent vertices, they are not allowed to get the same color. Okay? And so, yeah, so this was obtained a long time ago. It's a recurrence relation that should have some combinatorial interpretation, but at the moment, nothing of that kind is known, and the only proof is by this recursive method. It's a big thing, the proof. Yeah, Asia, oui.
Triangulations of the sphere or any genus?
Yeah, it's planar triangulations, and almost all my lectures will deal with the planar case. So yes, triangulations of the sphere. Okay, so what should I add? So as I said, there's 20 hours. That's a lot of time. And I certainly don't want to lose my audience. So I'm not sure how familiar you are with enumeration. And I'm sure that some of you are not familiar at all with enumeration. And so I ask you to talk, to ask questions, and stop me if it goes too fast. I also see that some people know that as well as I do, so too bad for them. And so really, I mean, stop me. I see Andrea is not here, so you'll get the opportunity to ask questions. Okay, do you have questions? And you have to stay awake, because as I want you to talk, I've prepared exercises. So be ready. Okay, so that was somehow some introduction. So today we have two lectures. So essentially one this morning and one this afternoon. So this morning we'll learn how to write functional equations for maps, and in fact for planar maps, following what Tut did some 50 years ago now. And essentially this afternoon we'll try to know how to solve these functional equations. Okay, so let's start with this first lecture. approach. And if I write too small, if you can't read, again, just tell me. Okay, so we'll start very classically with some definitions. And first, of course, what a map and more, especially a planar map is. So a planar map is an embedding of some multigraph, and by multigraph I mean that we allow both loops and multiple edges. For instance, so an embedding in the sphere and this is in fact a combinatorial object, meaning that this is taken up to orientation preserving homeomorphisms. So for instance, this is a planar map, so it's drawn on the sphere. Of course, I'm drawing on the blackboard. So you have to think that this infinite trunk around is just one face of the map. So talking about faces, so we have three main elements in a map. So we have, as in a graph, we have the vertices, we have the edges, which, as I said, can be loops. And we have something that graphs do not have, namely the faces, which are the connected components of the sphere that you get when you erase vertices and edges. So for instance, here, how many faces do you see on this map? That's my first exercise. 4. 1, 2, 3, and the big one. Yeah, okay. So vertices and faces have a degree, which is the number, so the degree of a vertex, say. It's the number of half edges incident to it. So that's important, it's half edges. So for instance, this vertex has degree 2. It is incident to just one edge, but to 2 half edges. So let's write the degree. So that's 2, 1, 1, 2, 3, and 2. Okay? Yeah?
Doesn't the first vertex have degree 5 because of the other?
Oh, that's very true. Thank you. 1, 2, 3, 4, 5. 6, someone is saying 6. 1, 2, 3, 4, 5, 6. Ah, good students. Thank you. Are there any more like that? No, not yet. Okay, so not only vertices have degrees, but faces have degree as well. And the degree of the face is the number of, well, edges or half edges, but say edge sides. Incident to it. So what do I mean by an edge side? So previously, to define the degree of a vertex, I've cut an edge into 2 half edges like that. But you can also cut it in 2 edge sides like that. So you have one side here and one side here. So why am I saying that? Well, in order to be able to say that this face here has degree 1, 2,
3, and 4. So that's really the length of the walk that you do when you walk around the face. And one edge may occur twice in this walk. So next exercise, the degree of the outer face is what's the degree of the outer face here? I want to hear you. 5, says Lin Chao. Thank you. Okay. So what else should I define? Well, when we count things, we don't like to count objects that have symmetries. For instance, if you take this small map, 1 vertex and 2 loops, there's no way to distinguish this loop from that one. They play exactly identical roles. And so in order to avoid this, and to avoid all this Burnside lemma and whatnot that you need to use when you want to count objects that have automorphisms, we are going to consider all the time rooted maps. So what is a rooted map? So it's a map in which you distinguish a corner. And what is a corner? So that's an incidence between a vertex and a face. So for instance here, well, maybe I will start from my map. So I could say that here, so at this vertex, I have 2 corners, the incidence with this face and that vertex with that face. So I could choose, for instance, this corner here. And that would be a rooted map. So here, I could choose, so I have, as we said, degree 6, and there would be 6 ways of rooting, so I'm only drawing some of them, of rooting this map at this vertex, and so on. Here there would be 1 way. So for instance, if I get back to this example, so I said there was no way to distinguish between these 2 loops, but as soon as I choose one rooting, then when you walk around this face, starting from the root corner, then you see a first loop and then a second. And they do not play any longer the same roles. And so in fact, it can be proved that these rooted maps have no automorphism left. Are there questions? Yeah?
So for that map, there's 4 different rootings of that same vertex based off of where you put that arrow?
There's just 2. So for instance, these 2, they give the same map. It's just this. And then, okay, so these 2, they are the same. And then the other one would be that one. Yeah?
Clarify the degree of the outer face in the previous example, because don't you count this half edge twice to become 6?
So say I start from here, and I walk around the face. So that's 1 step, 2, 3, 4, 5.
You can't loop from
Yeah, so here this edge is just visited once along this side. Whereas this one, when I walk around this face, it's visited twice along both sides of the edge. Is that clearer? Yeah. Are there more questions? No. Okay, so now we've killed automorphisms, and probably the last thing I want to define is the dual of a map. Yep. God, this is falling apart. It's terrible. If at some point we can find something a bit better than that, it will be a plus. Okay, so the next definition, as I said, is the dual map. So it is obtained, maybe I'll draw my map again. So it's another planar map. So say I have rooted this one. So very often, that's one convention. Yeah, I should ask something about the root. So once you have rooted a map by choosing one incidence between a face and a corner, so this defines naturally a root vertex, a root face, and also a root edge, which is by convention the first one that you meet when you start from the root corner and walk around, say, this face in the here in the counterclockwise order. So I should tell you about another convention. Very often, but not always, we will draw the root face as the outer face. But of course, this is just a convention. So with this convention, when you walk around the outer face, the first edge you meet is the root edge. And in fact, very often, and especially in most of the talks that we heard last week, for those of you who were here last week, this is the usual convention. This is also the one that Tat was using. So choosing one edge and orienting it. It's completely equivalent to the routing I'm telling you about. But for several reasons, I prefer this one, which was invented, if one may say so, by Olivier Bernardi some years ago. But they are both completely equivalent. Okay, so now I come to the definition of the dual. So to construct the dual, I put a new vertex, say green. Can you see that? What's the colors that you can see? What's better? That's green, that's pink. Blue. What's the louder? Pink. Okay. Because last week I realized that from a distance, white, blue, yellow, and whatnot are essentially the same color. So my dual map will be pink. So I put a vertex in every face. So I have 4 faces and 4 vertices. And now for every edge of the original map, I draw its dual, which is an edge that joins the 2 faces on the side of this edge and crosses it. So where am I? Here. So now I should join this, this, and now here. So on both sides of this edge, I have the same face, and so this creates a loop here. Am I missing some edges? Which one? Oh, yeah, here the little one. So this is going here, I guess. That's all.
When you designate the root this way, how do you know that that's the root edge and not the other?
That's a convention. I decide of a direction counterclockwise. I could just as well take another convention. And conversely, if I had in the usual touch setting, when I have the usual routing, which consists in distinguishing one edge and orienting it, I can get backwards. So there's some, by saying that this one here is the root corner. So this is,
By convention, the root edge is the first.
yeah. Okay, and then I have to root this dual map. And it's quite convenient because here I had one incidence between that face and this vertex. And I want to distinguish the same or the dual incidence. So I should essentially just flip this edge. That's a bit unfortunate here. So this corner here between that face and this vertex has become, I guess, this corner. So every face of the original map becomes a vertex of the dual, and conversely, every vertex of the original map becomes a face. Okay, so in general, so this is a bit unfortunate, but in general, when you want to root the dual edge, so you had a vertex here, a face there, and so just rooting the dual consists in doing that. So that's one of the charms of these alternative ways of rooting maps. Okay, how is it with duals?
It's the same for the first edge, again the one on the right, when you take the dual.
Yeah, so yeah, I define the root edge as the first when you go around the face. It's a bit less convenient to define how you root the dual when you use this convention. Yeah?
Does the root edge in the dual no longer necessarily correspond then to the root edge in the original graph?
I think it doesn't, yeah.
Okay.
So we can check. So say we had this, so the root edge was this one, and now we're pointing there, and the root edge is this one, and I see no reason why it should be the dual of this one. So let's see here. Yeah, so here we have an example. The root edge is this one, and it's not the dual of that one. So, more questions? Nope. Okay.
Sorry.
Yeah.
If you dual again, this one you will get the original one. Right?
Yeah, because you've taken the same incidence face vertex, so you'll get back to it. So the last thing I want to say about maps is just to give you this Euler's relation. Let's erase that nice theorem. So I state it for the moment in the planar case. So it tells you that for any, oh, merci beaucoup. So for any planar map, the number of vertices plus the number of faces is equal to 2 plus the number of edges. Okay. And in general, so we've not defined maps on a general surface, but in general it's 2 minus 2g. So suddenly I have a doubt. C'est bien ça. Thank you. So this would be the formula in genus G. So the only use we'll make of this formula is that it will be equivalent to count, say, triangulations by the number of vertices or by the number of faces or by the number of edges by combining this plus the fact that you have a triangulations, but we'll come to that. Okay, so these were my definitions about planar maps. And now we'll have a few more definitions about power series, because we're going to count these beasts using power series, formal power series. Oops. So if you have a class or a set, say S, of objects, so for instance planar maps, equipped with some size, for instance the number of edges, so what is the size? It's say I denote it like that. And you assume that the number of objects of size n is finite. Then what we call the generating function of this set S, counted by this size. So it's a formal power series, so it's a series in, say, some variable t, which is the sum over every object of S, so some structure of t to the size of S. Okay. So every object contributes some monomial in your generating function. And so you can think of this differently as the sum over all possible sizes of t to the size times the number Sn, which is the cardinality of the set of objects of size n. Okay. So how many of you, should I ask the positive or the negative questions? How many of you have never played with generating functions and basic enumeration of objects? None. Excellent. Okay, so you are all, did I see? So there's one hand here. Okay. So you are very familiar with that. So this is the basic generating function, and yeah?
Do you have any restrictions on Sn must be finite or S0 must be?
Yeah, so Sn must be finite at this condition. You only want to have finitely many objects of size n, so that the coefficient of t to the n here is finite.
But S of 0 must be 1? Or?
No. Well, often it will be either 1 or 0, but who knows, we could have different conventions. And so on many occasions, we will count our maps according to several parameters. For instance, the number of edges and degree of the root vertex or whatnot. So we will have also some multivariate generating functions, like for instance the sum over all objects of t to this size and then some x to some additional parameter and maybe y to some third parameter and whatnot. And so in this setting, what you'll have here, and that's important, so the coefficient of t to the n, which used to be some integer, is now counting objects of size n according to two more statistics. And what you'll have here is a polynomial depending on n in x and y. For instance, if you count maps by edges and root degree or whatnot. So some notation. So if I have some field of coefficient, say f, what I denote rather classically f of t is the ring of polynomials in T with coefficients in F. I will also use this notation for rational functions. Same story. And for formal power series, I will use this double square bracket. So for instance, this thing here, can you tell me to what space it belongs to? Sorry? Yeah, so I will be. So let's say it's Q, the set of coefficients. So let's say I have Q, and then you can all speak. Yeah, so I have polynomials in what? X and Y. And then ups. And then here. Okay? Yeah, but sometimes I take reciprocals, and so, but in practice. Yeah. So this is. Yeah. So here, yeah. So this, this includes some Lorentz series, if you want, where you can have finitely many monomials with a negative power of t. And so this is a subset of Q of x, y, t, meaning power series in 3 variables, but it's smaller, of course, because this one contains the sum of x to the n, which this one doesn't contain. And so at some point, we'll play with several spaces of power series like that. Okay, and the last thing I want to define about this power series, there's more. So the last thing I want to define is a certain hierarchy of power series that we like to play with when we count. And roughly speaking, this hierarchy tells you how your solution, your generating function, is complicated. So this hierarchy goes as follows. Formal power series. So the simplest of them are the rational series. So ratios of polynomials. So that's the one variable setting. Then comes a more general class, which is the class of algebraic series. And this means that you have a certain polynomial in the variable, and your series that vanishes. So of course a non-zero polynomial, otherwise there's not much information. So that's non-zero. Then comes a third class, which is called the class of definite series. So I should say that in the first part of the talk, when we'll count maps without any additional structure, we'll be systematically in this world of algebraic power series. So that's decently simple power series that are, for which we have many tools, say for instance to get the asymptotic behavior of the coefficients and so on. So the definite series are those that satisfy a linear differential equation. So of the form, so the sum, so you have polynomial coefficients, and then you have the ith derivative of your series, and this should be 0 for I from 0 to some order d. And it can be proved indeed that every algebraic series belongs to the definite world. So this is indeed a larger class, still manageable, say, from an effective point of view. So say this is the world in which planar maps live. And then there is a fourth class that some people do not like so much, but we'll have to deal with them, which is the class of D algebraic series. So D stands for differentially, here and there. And they are those for which you have a polynomial equations relating the variable t and then a number of derivatives of your series. Again, of course, a non-zero polynomial. So obviously it's more general than those definite series for which you wanted to have a linear differential equation, whereas here you just want some polynomial differential equation. And so I started this lecture by saying that that this problem of counting properly cube-colored triangulations could be solved by a certain recurrence relation, which was not linear. And in fact, underlying this result is a differential equation, which is nonlinear of second order for the generating function. So it is order 2 and degree 2 as well. So one instance is a cube-colored triangulations. And so when we'll move from the first part of my talk, we'll essentially move further up in this hierarchy. And of course, there are all the unsolved problems that possibly lie beyond that. I don't know. OK, so this is enough for definitions. Where are we? So at some point, we'll have to define whether we want to make a break. So, but maybe not yet. Other questions on this part? No. Okay. Did I say everything? One piece of notation again. So if you have your series S of t, which is the sum of t to the n Sn, the nth coefficient in S of t is denoted with those square brackets. And what else? Maybe going back to that, I would like to clarify, since we will be dealing very often with multivariate generating functions, I would like to clarify what are the corresponding notions if you have a multivariate series. So where's my pink chalk? Here. So here, say if you have a series in T and X, well, here's the generalization is the one you're thinking of. You want a ratio of two polynomials in T and X. Here, for the algebraic series, you would simply like a polynomial in T, X, and your series to vanish. So as you would guess, so this is being algebraic over the field of rational functions in T and X. So what happens here is more interesting because if you want a good definition that has nice properties, including closure properties, what you need to require, or one way of getting nice properties, is to require that you have one linear differential equation per variable. So not only you want, what should I write? So you want, if you have two variables, T and X, you want a differential equation of this type where you allow polynomials in X. And here you have only derivatives with respect to T. But you want also to have another family of polynomials, Qi, with a linear differential equation in X. And here, it will be the same. When we say something is differentially algebraic, you'd like to have an equation, differential equation with respect to T and one with respect to X. Okay, so this was a long series of definitions. And I finally come to our first counting problem. So say I had a 1, so this will be 2. So counting general planar maps. So this is really what Tutt was doing in the 60s, so a long time ago. And what he did was to describe recursively those maps by having the size increase or decrease. and to encode this as a recurrence relation on their numbers, essentially. So the basic idea is that he adapted to maps what you would do if you wanted to count trees. And I realized I forgot to define trees. So a tree is a planar map with just one face. Okay? So that's just the outer face. So you all know what a tree is. And so there is also a root corner. And so this is the root edge. Okay. So if you want to count trees with n edges, say that the corresponding number is a of n. Well, what you do is you write a very standard recurrence relation by considering what happens if you delete the root edge. Well, you're left with two trees that you can root, so everything is rooted, that you can root in some canonical way. And so using this observation, you write that a tree with n edges is obtained by taking to the left a tree with I edges, to the right a tree with j edges, provided that I plus j is n minus 1. And you need some initial condition saying that you have one atomic tree reduced to a vertex and no edge.
So in your definition of map, they're all connected.
Oh yeah, I forgot to say that. That's very important. Thank you. Yes, they are connected. Connected multigraphs. Okay, so that's the standard convolution recurrence relation for trees. So since you are all familiar with enumeration, you know that this can be converted into a functional equation for the corresponding generating function. And so what this recursion says is that this series has some initial term, 1t to the 0, corresponding to this, say, atomic, I sometimes call this the atomic map or tree. And then come the bigger objects, which are obtained by concatenating the root edge and two rooted trees. So are you all familiar with going from recurrence relations to this kind of simple functional equation? Yeah? Okay, good. So in what follows, I will, well, maybe not in this example, but starting from the next one, I will always directly write functional equations rather than recurrence relations. But if at any point you don't feel comfortable with this, you have to think that if you sit for a few minutes, write the recurrence relation and convert it into a functional equation, you'll find what I wrote, hopefully. Okay, so this idea of TUT is to try to do the same thing with maps rather than trees. So we take a map, assuming it's not the atomic map, we remove the root face, the root edge. What's left? And what happens is that there are two cases. Of course, we had the atomic map, okay? And then there are two cases, so either That's my root edge, the root corner. And either removing this root edge disconnects the map. Yeah?
So in rational series, are you thinking there's a functional equation as well? Or, I mean, so for all the other ones, you had equals 0. And for rational series?
No, so that's the value. So I just mean that my series can be expressed as a ratio of two polynomials.
Okay, but for the other ones, it somehow has a functional equation set it equals to 0.
Yeah. Well, if you want here, you have a functional equation of this type, but of degree 1 in S. Yeah. Do I understand what you're saying? Yeah. Okay, so maybe the removal of this root edge disconnects the map, which is what was happening for trees. But this may not be the case, and you can have a root edge. And then when you delete it, well, you still get one connected component, which I usually draw like a bean like that. And so the idea is to count separately those 2 or 3 types of maps. So, okay, so, we want to count them by edges. So M of n is maps, rooted planar maps with n edges, the number of such maps. Okay, so this one will contribute, well, 1. Now, in this case, what I'm doing is that if I erase the root edge, I have 2 maps, and the second one can be rooted canonically at this corner. And so I'm just concatenating 2 maps in the same way I was concatenating 2 trees here. So in this case, I get again the sum for all pairs I and j that sum to n minus 1 of m of I, m of j. Okay? Every pair of maps will give me, by adding one edge between them, a map of this type. I will often call this an isthmus. Maybe I should call it a bridge, simpler word. So that's the bridge case. And then this is somehow the new case that makes maps different from trees. So, okay, I erase the root edge and I get a map. So, okay, of size n minus 1. But the problem, can you see what the problem here is when you want to count maps using this description? What should I write here? How many maps of this type are there? Is it m of n minus 1, for instance? Yeah. Who said that? So the problem... Sorry?
What did he say?
So he said that I should, so he went very fast. So he should say that I should remember the degree of the root face, or also called the outer face. So why is that so? So when I erase this, so it's no longer there, okay, I get a map of size n minus 1. But the problem is that several maps of size n will give the same map of size n minus 1. It's not 1-to-1. And the question is, if it's not 1-to-1, it's how many to 1? So I'm asking you, it's how many to 1? So how many maps of size n? So given a small map m prime, which is this bean here, how many maps of size n give it by deletion of the root edge? Or said in other words, if I want to go backwards, so I have this m prime with its root corner, in how many ways can I add one edge? whose deletion will give M prime.
You assume that the next map you get is rooted at the end of the...
Yeah, so I leave, so that's one thing that's convenient. The root corner stays where it was. So that's why I prefer rooting here than rooting on the root edge. Otherwise, you have to define what is the next root edge and so on.
So the degree of the outer face minus 1.
Alors, who is speaking? It's, yeah. So you say degree, okay. So let's take a small M prime. So that's my M prime. So outer face or root face has degree 3. And I ask from how many maps with 4 edges does it come from? 3. Okay, so I could have had, this could have been my root edge indeed. Then what? This could have been my root edge. This could have been my root edge. Allez, les enchères. And then, in fact, there's one more. This, I should draw it again. So that's the bean. If the root edge is like this, then certainly its deletion gives the little triangle M prime. So in conclusion, if M prime has outer degree D, how many times do I obtain it? D plus 1. Okay. So what we want to write here is, say, the sum over all possible outer degrees of the number of maps with n minus 1 edges and outer degree D. There should be a D plus 1 factor, certainly. Where should I put it? Otherwise, it's simple. Thank you. So every map of this type comes from D plus 1 bigger maps. Okay? So what is this telling us? Well, it's telling us that we cannot really, at least using this simple recursive description, we cannot really write a recurrence relation for the sequence M of n. It seems that we should have to count, whether we want it or not, we should have to count those maps according to this additional parameter, the degree of the outer face. Okay, so let's agree to do that. And from now on, I will move to formal power series rather than arrays of numbers, M of n d. So I will define a bivariate power series in T and say Y, which is the sum over all maps rooted planar of T to the edge number Y to the outer degree. And for reasons, okay, no. And so I will need to consider for every D the coefficient of Y to the D in this series. So you see this depends only on T. So this is the generating function of maps with outer degree D. Okay? So I just need the notation for this thing. Okay, so now we are ready to start again. So I say that there is this simple atomic map which has no edge and outer degree 0 by convention. Then comes the bridge case, so where I take these two maps on both sides. So the edge number is essentially additive, except that I should also count this edge. And quite conveniently, the outer degree is also additive, except that I should add 2 for the two sides of this edge. So what the bridge case gives me is a factor t for the new edge, a factor y squared for its both sides, and then the same series squared. And this is the exact counterpart of what I had for trees, with one more statistics here, the outer degree. And then what? So then I take a small map, the M prime, which has a certain outer degree d. So I take this map. Its generating function is md. This is this notation. And then I want to add a root edge, which will be a non-bridge. And so we described here in how many ways. So we said in d+1 ways I can add this root edge, but now the question is more precise. The question is, what is the outer degree of this new map?
Question about the picture here, how we counted the ways the outer edge.
Yeah.
It seems the way we've drawn it, it changes the outer degree.
Yes, it does.
Okay.
So for instance, so if I start from this bean, and we have to record this, that's precisely where we stand at the moment. So say this is my M prime. So if I add just a little loop, what's the new outer degree? D+1. So if, say, this was the next vertex, if I add this edge, what's the new outer face? It's still D, you said.
I guess doesn't it depend how many edges are between the first?
So that was the first vertex, the first corner, more precisely here. So that's D. And it goes on and on until the case where I add a big loop around my M prime, and then it's just 1. So that's what we are about to write. So if I add just a small loop, the map I get has outer degree D+1. If I just go one step further and insert in the first corner, I will just duplicate essentially the root edge of M prime, and so on, until the case where I do a big loop. So what we are saying here is that this map M prime, it was coming from D+1 bigger maps. And here we are saying something more precise, saying that they had respectively outer degree D+1, D, D-1, up to 1. Okay? Yep? So here, this is just counting those maps M prime by the edge number. So at the moment, I have no y. So all the y information is encapsulated here. Okay? Okay, so now we are in business. So this is just a geometric sum. So what should I use? It's y, and there's a factor y, and then y to the D+1 minus 1 over y minus 1. Okay, so I will just copy this, so it's the sum. You should have complained, I forgot one term here. T, thank you. So it's the sum over all these of md of t then there's this factor y, and then y d plus 1 minus 1 over y minus 1. So I'm just copying the third term in my equation. And so what do we have here? So if we just take the first term, sum of md yd plus 1, well, up to a factor y, this is just my original function. So ty, so here I will have y m of ty corresponding to this part. And then how can I write this other sum here with the minus 1? M of t1 minus m of t and 1 divided by y minus 1. Okay, so that's the functional equation and obtained by the removal of the root edge. So I want to write it down again, maybe. So, and at the same time, comment on it a little bit. So first, are you okay with that? Yep. Okay. So what's happening here? So I have this bivariate series M, which is, I hope, characterized by a functional equation, which involves, and that's the most characteristic part of this equation, which involves its specialization when y is 1. So what I'll do is I will lighten notation by denoting, by dropping the dependence in t, and this I just write m of y, and we say, following terminology introduced by Doron Zeiberger, that the variable y is catalytic. And as far as I understand, the idea behind this terminology is that even though you were not interested in this parameter, you were forced to introduce it to get something. That is, to exploit your recursive description of maps and translate it into some functional equation. So that's Zeiberger. What should I say next? So now my equation reads like this. And I claim, and this is of course important, that it, in a sense, solves a problem in that it characterizes a series provided you tell it's a power series in T. So I want to explain this statement. So it seems a bit strange because you have, almost two unknowns in this equation, m of y and m of 1. But since you know that m is a power series in T, you can think of extracting recursively the coefficient of t to the n in this equation. And so given that you have a factor t here and there, you know that the constant term in t must be 1. And now if you assume that you know this series m of y up to the coefficient of t to the n minus 1, then you can, again, because of these factors t, you can compute the nth coefficient. Yes?
Your equation is linear.
There should be an m squared. Thank you. Would be easier. Well, not completely obvious either. Okay, so that's an important point. We have a unique power series solution of this equation. Now, well, there are some obvious things that we could do. Say we want to determine m of y, or it suffices to determine m of y, which is just the generating function of maps counted by edges, forgetting about the outer degree. So what could we do? So either the first temptation is maybe to let y go to 1 here. So this gives you m of 1 in terms of essentially the derivative of y, m of y, taken when y is 1. So you'll have your unknown function m of y given in terms of m prime of 1. And you could iterate that, but there's no obvious solution. And another temptation is to multiply the whole equation by y minus 1, and then set y to 1. But if you do that, so this term multiplied by 1 minus 1 will cancel, this one 2, and here as well. So if you multiply by y minus 1, you get something that's tautological when y is 1. So what I claim here is that how to solve this is not completely obvious. And so we'll see this afternoon what we can do with that. Okay, so before we move to more examples, I want to tell you that there's an alternative construction, recursive description of those maps based not on the deletion of the root edge, but on its contraction. And this should be dual. And this should remind you of the Todd polynomial for those of you who know it, contraction, deletion. But still, I want to write the details of that, because at some point, when we move to maps with a structure, we'll have to use the two constructions, deletion and contraction of the root edge. So let me briefly describe the contraction counterpart of this derivation. So now so what is the dual of the outer degree, the dual parameter? If I take a map, I take its dual, the root degree of the original map, how is it described in terms of the dual map? Louder? Yeah, the degree of the root vertex. So let m twiddle of t and x be the generating function of all maps counted by the edge number, and x to the degree of the root vertex. So first of all, well, we know what this series is precisely by duality. This should be the series we have just studied. Because if a map contributes t to the e, y to the x to the d in this series, its dual contributes that in the other series. So is that clear? That these two series should be the same. So what I'm doing now is that I write, in fact, the same functional equation for this series, but with a different combinatorial argument, which is just the dual of the original one. So what do I say if I want to study this series? I say, again, there's the atomic map. Then come maps in which essentially I cannot contract the root edge because it's a loop. And these maps I will split into two rooted submaps, as I was splitting maps in which the root edge is a bridge into two submaps. And then what's more interesting is the third case. So the root edge is not a loop. So that's my root corner, and here I have some additional vertices that are incident to that. This may be a bridge. And then what I do here is that I contract the root edge instead of deleting it. So there were two half edges incident here and three there. So this is the map M prime that I get. And now the interesting point is I will get several times this same map M prime if I contract the root edge in all maps of size n. And how many times do I get a given map M prime? So it should be the same answer, essentially. Philip, you're laughing. You know the answer. Yeah, so if the degree of the root vertex here is d in M prime, then it comes from d plus 1 maps as before by contraction of the root edge, and we can draw them. So maybe you're starting from this, and you put all. So the root vertex will keep its 5 incidences. So this map, by contraction of the root edge, gives this M prime. But there's more. Maybe you could just keep at the root vertex 4 half edges, and the last one is sent here, and so on, until the case where the root vertex has essentially given all these 5 edges to the new vertex and ends up having degree 1. So that's exactly, so what's happening to this edge that you're contracting is completely dual to what was happening to its dual edge in this construction. And in particular, now if you look at the degree of the root vertex of these maps, they will again range from d plus 1, d up to 1. And so when you write the equation, the corresponding equation for this new series M twiddle, you'll get exactly the same terms. And it should be so, because it's the same construction, but described on the dual. OK, and now I see that you won't have a break. Sorry to say. OK, so we've written our first functional equation for planar maps after an hour and a half. And so now so of course there's still the question of solving it, which will be deferred to this afternoon. But what I want to tell you now is that this approach, which combinatorially speaking was trivial. I mean, you delete the root edge and you look at what's left. What could be simpler? I mean, it's not sophisticated, but of course there is a cost, namely this kind of divided difference here. So what I want to say now is that this is very robust, and that there's many, many, many families of maps that you'll be able to count, or for which you'll be able to write a functional equation by using this approach. So we'll do a few examples. So that's a part, say, I guess 3. This is robust. So here we've counted all maps. And now, of course, we want to count restricted families of maps, smaller families of maps. And the kind of conditions that you can impose on your subfamily of maps and that go nicely with this recursive description are constraints on phase degrees and, to some extent, on the connectivity of the map. So we'll start with an example where you have a constraint on phase degrees, namely the example of triangulations. So by triangulation, I mean a map in which every face has degree 3. So this includes strange maps. So for instance, something, remember this face here? It has degree 3. 1, 2, 3. So of course, the outer face is not a triangulation, but this would be a triangulation in this terminology. Every face has degree 3. So now if you think of a triangulation and deleting the root edge, maybe the outer face will no longer have degree 3. And so this is why to count these, we have to introduce near triangulations. In which we require all finite faces, that is all faces except the root face, to have degree 3. So every finite face has degree 3. So for instance, so what should I do? Maybe. So this pair of glasses has outer degree 2. And it is a near triangulation because each of the two finite faces has degree 3.
So you mean now infinite face is the group outer face?
Sorry?
You mean that infinite face is outer face?
Yeah. So that's every non-root face, maybe I should say. Okay, so let's define a generating function for these near triangulations. So say T, counted by edge number and outer degree, which again I will denote simply T of y, ignoring the dependence in the main size variable. So that's the generating function over all near triangulations of T to the edge number and y to the outer degree. Okay, and now comes your first exercise that you can discuss between you. How can you recycle this to write an equation for this series? So maybe we can discuss the first steps. So, well, I guess you all agree that we can consider this, if we need, as a near triangulation. Then what's the contribution of near triangulations in which the root edge is a bridge? In other terms, what condition do you need on each of these two pieces for the connected thing to be a near triangulation? Yeah, so it suffices that these two pieces have themselves finite faces of degree 3. So I will get exactly the same contribution, except that my M has become a T. And then comes the more interesting term. So I remove the root edge and assume there's just, Nicolas, there's just one piece left, this M prime. So it's also a near triangulation, that's fine. All its finite faces were finite faces of M. How many times do I get a given near triangulation? So that's the question that we now. Yeah, so things had to look. So that was my root edge, and now this face was finite. So that's my bean M prime that's left. Yeah, so here I hear that I get once every near triangulation. Do I get every one? Sorry? Yeah, okay. So the degree here should be big enough. That is, for instance, if my near triangulation M prime is like this, that is, has outer degree 1, there's no way I can create a face of degree 3 by adding just one vertex around, one edge around. So are there more outer degrees for M prime that I should forbid? For instance, if I take some M prime of outer degree 2, will I be able to create a triangulation, a near triangulation from that? Yes. So, okay. So what I need to do, I have my M prime, and I walk 2 steps around its root face, and I add my edge here. Okay, so how can I convert these observations into some term here in my functional equation? So I can give you one term, T. That's for the root edge. So then what should I write here? What should I take? Yeah, so maybe I should write this as before, as y to the d, t d, which is the generating function of near triangulations with outer degree t. So I'm being told that I take all near triangulations except those that have outer degree 1, from which there's nothing I can do. And so their generating function is some contribution in that, namely y t1. Now there's one thing that we should take care of. That is, how does it change the outer degree? Sorry? Yeah, it loses 1. Okay. Okay, so it's an equation essentially of the same form as before. It's quadratic in the main series. And instead of having m of y minus m of 1 divided by y minus 1, we have another type of divided difference, now around y equal to 0 in a sense. And we've just subtracted, sorry, there's one more objection. Yeah, okay. There's also this. So say y0, t0. Indeed, if I start from the atomic map here, there's no way I can construct a triangular face. So this is just minus 1. So what I did here, I took t of y, subtracted the first two terms of its expansion at 0. One of them was fairly simple. The other one, we don't know what it is, and that's the one we'd like to determine. And I've divided by 1. So here's another example of an equation that you can get using this TATS approach. And now we can go on with variations on this. So this was for triangulations. Now I want, and we've seen this class of triangulation several times last week. So now I want to consider triangulations of a polygon, say. And by this, I mean that the root face is simple. Meaning that when you go around it, you see just one every vertex. And in other words, what you wouldn't like to see is pieces like that. So this is not simple. And this is simple. That is, you should think of the outer face as really some polygon. And you want to triangulate this. Okay, I'll do something simple. But
simple means you cannot disconnect by
yeah, one vertex. Well, it's just the outer face to be simple. I don't want the whole map to be non-separable. Yeah, of the outer face. So here, when I go around, I see twice this vertex, for instance, and this is something I don't want. I want something fat with no wasp waste. Okay, so let's call P of ty, or P of y, P like polygon, the generating function of these triangulations of polygons. And again, I want to record the edge number and the degree, the outer degree, the degree of the root face. And we like to use the same ideas to write an equation. And I let you choose this for a few minutes. So can you have a bridge in such maps? No. So the second case will be fairly easy. Well, I guess the only way you can have a bridge if you have this thing that, well, should we call it, by convention, we'll call it one of these triangulations. Okay, so the main question is in this third case, which was also drawn here, but is no longer drawn here. So say we have the root edge. Here there's a triangular face. And we have the map around. So you delete the root edge. And then you get a new triangulation. And question, is it a triangulation of a polygon? So it's certainly a near triangulation. But is the resulting outer face still simple? Yeah, so it's not always simple. That's the problem. And so the only thing that can happen is that the third vertex of this face, which is on the other side of the root face, belongs to the boundary of your original map. So somehow you have a map with two ears here. And so if I delete the root edge, I get a near triangulation of something that's not simple. But of course, adding this edge creates a triangulation of a polygon. And then there's the other case where the third vertex is not on the boundary. And so the bridge case has essentially vanished, reduced to nothing. But now the distinction between two cases has to be done in this non-bridge case. Okay, so can you tell me, in the case where you have two ears, say T1 and T2, what is the contribution in my series of those maps? It's again some kind of concatenation. Yeah, you want to have a square, and you need to record the outer degree. So say you take two polygons, then one more edge, the root edge, and what happens? What should I do for the y that records the outer degree? Divide by y. Yeah, so because you had these two edges that are no longer on the boundary, but you have added one along the boundary. Okay? So that's this type of maps. And then for this one, well, we are saying that deleting the root edge leaves a polygon, a triangulation of a polygon. So this is really the same term as before, except that we are now with polygons. So we don't want to have something of outer degree 1. And I'll stop here, because now our initial condition, it's convenient not to choose this atomic map, but to choose this, because you'll see that this includes, as a degenerate case, the case where one or both of these ears are just reduced to a single edge. So you have to convince yourself that this is the right thing. So this has contribution t y squared. And so with this construction, I don't have any atomic map anymore, so I do not need to subtract one. Yeah. Sorry?
Do you need to subtract something from the square, u y square? Because
You mean subtract something additional from here? Here? No, I think I'm happy. So whatever I take here for choosing these two ears, and including if I take just one edge, I will obtain a triangulation of a polygon. Do you have in mind some case where things would...
you don't have an atomic connector, please.
No, I don't. But in fact, in this construction, on both sides, I never get the atomic map. So that's fine. The smallest map I can get is the one reduced to a bridge. So sometimes, this often happens, that you have to fiddle a bit with your initial conditions and with your definition to get a nice functional equation. So I'll write this equation again. So for triangulations of a polygon, you have a slightly different initial condition. Then you have the case with two ears. And then the case where you get a simple map. Okay, so that's still one example of an equation of the same type.
Sorry?
Yep.
One dot is not a convention.
Yeah, so that's my convention here. Of course, I could decide that I want it, so then I would need to add 1 here. But then here I would have p of y minus 1 squared, because these ears cannot be reduced to a dot. The smallest thing they can be are just one edge. And here I would have to subtract 1 as well. So it's adding 1 on one side and then systematically removing it. So forget about the atomic map. Okay, so we get equations that are polynomials in the main series with some specializations. And then before we end this first lecture, I want to let you feel what may happen if, for instance, if you just want phase degrees 7. So we've done triangulations where the phase degrees had to be 3, and we had taken out in our construction when we were with this M prime and adding one edge to create a triangle here. We wanted this map M prime to have outer degree at least 2. In order to create a triangular face. Now, if I want to create faces of degree 7, what will I get here? So I have my root edge, and then I want 1, 2, 3, 4, 5, 6, 7. So what will be the counterpart of this term? What will happen? If I take an M prime that has degree 4, will I be able to do that? No. 5. With 5, I can create something of degree 7, a face of degree, nope. So this M prime, if I want to create here a face of degree 7, needs to have at least outer degree 1, 2, 3, 4, 5, 6. So what I would get, say for this new class of maps of degree 7, I would get this. It's not a T, it's an S. So what I mean with this example is that you shouldn't be surprised. So far in all our examples, we had the main series and one additional series that doesn't depend on Y. But in general, you should expect to have several of these series that do not depend on Y. For instance, S1, S2, and S5. And another observation that I want to make is that so far we've only seen quadratic examples, and there are indeed many, but that's not all what you see in those equations obtained by a recursive method. And for instance, if you think, so the first historical examples of that type was for quadrangulations of a polygon. So as before, we have a simple outer face, 1, 2, 3, 4, 5, 6, 7, 8. And you want faces of degree 4 inside. And so, okay, here we had triangulations of a polygon, so maybe we want to recycle this. And so what may happen here is that when you delete the root face, you have no longer 2 of these ears, but 3 of them. That will be one case. That is, you delete this face and you ask, is this simple? No, it's not simple, and it's given rise to 3 pieces. So here, if you count those quadrangulations of a polygon, you should expect to have a cube, because you are gluing together 3 simple quadrangulations. Okay, so I will stop this. So what I want to say is that we've seen a few examples of these equations, but in general, what you obtain from this kind of construction is an equation of the following form. So a polynomial in your series, which I call again M, but it's not necessarily the generating function of planar maps. And then you have a number, A1, A2, say AK, of auxiliary series that do not depend on Y. So in some examples, so that's the important thing. So in some examples, we had M of 1, or we had the coefficient T1 of triangulations with outer degree 1, or similarly, for triangulations of polygons, we had P1, and so on. And so their main property is that they just depend on a size variable. And then you have T and Y, and this is 0. And so this is what I call a polynomial equation with one catalytic variable. which is this y. And so that's the conclusion of this first lecture. This recursive method that Tutt used is very robust and yields, most of the time, not invariably, but very often, this kind of polynomial equations with one catalytic variable that we'll learn how to solve this afternoon. That's it.